Hello, welcome to our webinar on ARM Cortex-M optimized code generation from MATLAB and Simulink. I'm Tom Merkinen from the MathWorks, and it's my pleasure today to be presenting along with representatives from ARM Corporation and STMicroelectronics. I will begin with an introduction to model-based design, and then I'll discuss the new capabilities in Release 2013B that enable optimized code for Cortex-M cores. Then ARM and ST will present on additional capabilities that they provide to enhance and augment the optimized core code generation from MathWorks. We will conclude with a question and answer session. So as you watch the presentations, feel free to either submit questions in the WebEx entry form or just hold them and wait until the end of the event. So let's begin with the introduction. A typical embedded system development project includes system software and hardware engineering. They communicate ideas and specifications, code and hardware, but oftentimes the communication is blocked and bottlenecks occur because there's misunderstandings in the specs or the software is not compatible with the system or hardware designs. Model-based design helps remove these bottlenecks by providing an upfront simulation capability that includes your plant and your controller, or the environment and its application. You can essentially simulate the system on your host and then detail the software design using state machines and block diagrams until it's in a form that can be easily converted into C code using automatic code generation. The C code can then be compiled and linked and downloaded to any hardware that can handle standard C code. Along the way, a variety of test cases and verification activities occur, making it easy to confirm that the final embedded system matches the initial host simulation. When you look at the benefits of model-based design, you often may think of code generation as one of the main improvement opportunities, but generally the benefits come from early verification. If you look at this study from NASA, you can see that if you have an error in requirements, it costs an order of magnitude less to fix it if you find that in design versus if you find that much later in test. And this is a common notion that's been described by many software engineering books or studies over the years. And so what we've found is a number of our customers, such as those shown here, get quite a bit of their main benefit from having the automated verification activities occur early in the process. Generally speaking, the types of customers that can benefit from model-based design are those that have high degrees of algorithmic complexity, whether it's numerical filters or lots of logic paths. If you look at the types of applications themselves, they span from level A flight control systems from Honeywell to consumer surround sound systems to electric power grids and medical devices. These are just a few of the many examples of model-based design users in production. So the model is the focus of all development with model-based design, spanning from high-level executable specifications to detailed software designs through automatic code generation and continuous test and verification. Today we will focus primarily on the automatic code generation portion. To generate code from MATLAB and Simulink, you can use MATLAB Coder to get the code from MATLAB. This code is generally applicable for desktop applications, but it's nice, clean, portable code that can be used anywhere. Simulink Coder generates code from Simulink and also provides a real-time software framework that makes it easy to run rapid prototyping or hardware-in-the-loop applications on real-time machines such as XPC Target. Embedded Coder provides optimized code for either MATLAB Coder or Simulink Coder and produces code that can be used, for example, on high integrity systems because it has lots of commenting and traceability capabilities. It also has quite a bit of code verification and target optimization features, which I'll be describing shortly. Keep in mind that all of the coders by default will generate ANSI ISO-C because they can work on any embedded system. Generally, when people create a software application, they break it up into a basic software piece as shown, where you have your drivers and scheduler, your hardware specific components, and the algorithm, which tends to be abstracted from the hardware. In such a scenario, the use of code generation fits quite easily in that you can just generate code for your algorithm in such a way that it plugs in nicely with the basic software framework. This approach is called algorithm code generation. In order to make the algorithm plug nicely, you can use the embedded coder to specify the function prototypes, its input arguments, the name, as shown here. You can also specify the data interface information, such as storage classes, get-set-access methods, type definitions. So by controlling the function files and data, it is quite simple to just take the generated algorithm and plug it into an existing software framework. But another option to doing all this is to actually generate the full executable. By this I mean your algorithm model also contains device driver blocks that when you generate code from the model, you also generate code that will call the drivers. We're not generating assembly code. We're not generating the drivers itself, but you can specify in the model the driver interfaces and with a single button create the full executable as shown here. If you want to use this approach to model-based design, you can build these custom driver blocks using what we call S functions as shown. There are many ways to create an S function, which is essentially a wrapper around existing code. The most easy way is to use the legacy code tool, which allows you to specify the interface to your legacy code. As I mentioned earlier, things like the function call, definition, and the dependency files. And you specify this interface in a clean MATLAB file, and the legacy code tool will automatically generate the S function block for you. Whether you're using algorithmic or full executable code generation, you often want your algorithms to have optimized performance on your particular hardware. Now you can include that type of code using a legacy code block, as I showed earlier. But a new way to do it is to use the code replacement tool. With this, you would take, essentially you would map the standard definitions that come with Simulink for an absolute value or a trig function, and you would specify what the replacement should be. So perhaps an abs function runs much quicker on your hardware if you use the target optimized underscore opt abs with maybe different arguments. So with the code replacements, you simply do a processor mapping where you go through every function that has an optimized optimization available, or every math operation, or every fixed point operation, and eventually you create a processor mapping. Now we've done these in terms of ANSI, ISO, and GNU, and some AutoSAR capabilities, and we've had these for several releases, but recently we added it for the ARM Cortex-M, and this will be the topic I'll discuss in more detail shortly. So again, if you have a model with a number of blocks, you can replace all of these simply by picking your code replacement choice, such as the ARM, as I showed you in the previous slide. It would also replace the operations that may exist in Stateflow or the MATLAB function block. So an additional feature is If you're generating code not from Simulink but just from MATLAB Coder, you can get the replacements also using a MATLAB Coder to C capability. This is much cleaner, in my opinion, than creating a device-specific block like for an S function and removing all of the normal Simulink blocks and somehow wiring Stateflow to call your special block. So code replacements are quite nice because they support the full range of MathWorks major design tools. Another capability, once you have the optimized code, is to test the code. So if you have a model where you generate code for the algorithm, you can also generate code in a way that will allow you to test the code on the target. We call this processor-in-a-loop testing. As you can see in this diagram, you have some test inputs that are passed to the code running on the target, which does a single execution pass, sends it back to the model for closed-loop testing with an environment or a plant, and you do this non-real-time synchronization. Now the host needs to be connected to the target somehow, such as with the serial cable, and you need to establish the pill application using our APIs. But once this is done, you get quite a bit of features such as the ability to plot and log signals and compare the results from the host to the target, or do code coverage analysis using code coverage tool integrations that we provide, or you could do execution profiling analysis. Finally, if you prefer to generate code for the entire model and not just a block, you simply can change your simulation mode to do pill, and that will cause your whole model to execute in a pill manner. One of the reasons we talk about pill is it's a component that's essentially required for our certification workflows that have been reviewed and approved by the TÜV SÜD. By this I mean you need to show numerical equivalence between the model and the target, and pill is a nice way to do that for your algorithm. The standards that we support with the IEC Certification Kit include the automotive, industrial, rail, and medical standards as shown here for these products. If you need some assistance, we have an advisory service that can help you get started with the use of model-based design for these certified environments. So that's a quick explanation of model-based design from executable specification to certification. But let me run a quick demo for you. So I have here a fault-tolerant fuel control system that has some test inputs, the control system itself, and the engine dynamics. If I run a simulation, you can see that the behavior is shown in the scope where we have the fuel command into the plant and the air-fuel ratio being computed as an output of the engine model. Now if I start to inject some faults, you'll see that I have a different behavior in my command and my response. But let's go ahead and look at the state machine that's driving this response. So here's the state machine, here's my airflow calculation, here's my fuel calculation subsystems. But if I go ahead and look inside the state machine itself, you can see that if I have an oxygen sensor failure here, I increase my fail state and I went from a low to a rich fueling mode. Now if I have a second failure like a pressure sensor failure, you can see I'm in a multi-fail state and I've shut down the fuel command altogether. I can bring these back and I'll pause. Now one thing that's quite nice and new is if I want to have a high-level view of the behavior without drilling into the subsystems, we have a new feature called Content Preview, which I can actually look at the state machine behavior and preview other subsystems too without actually clicking inside them. So this was a new feature in Simulink, our 2013B. So if I run this same simulation again and start to cause some sensor failures, you can see the behavior as shown. So that's a nice new feature that I really like in 13B. So the point is, you've created an executable spec, you've interacted with it. Now it's time to generate code and target it in an embedded system. Now I don't want to generate code for the entire model, just the control system. What I'll do here is I'll just right-click and build the subsystem. But I've already done that, so let's just take a peek at the code. And you can see if I look at the different code snippets, you can click on the code and you can see the state machine, or you can click on the state machine and see the code. Now if I go ahead and click on a field calculation, as shown here, for example, you can see I have a switch statement that has these different operations. And you can do both numeric calculations and control flow calculations using MATLAB and Simulink. I can look at code metrics to get an assessment of the code size and complexity, as well as stack utilization. So the point of this demo is that once you have your executable specification, it's easy to get code. The question is, how do I now optimize the code even further? And that's where we're going to go to our next set of slides, which introduces the ARM Cortex-M code generation. So this little diagram shows we're generating ARM optimized code from Simulink diagrams. In particular, we're generating code for the CMSIS interface standard, which is a vendor-independent hardware abstraction layer for Cortex-M processors. It supports the Cortex-M family from M0 through M4 and has target-optimized basic math libraries as well as optimized DSP libraries. So here's an example of the basic math support, where you have maybe a Simulink model with sines and cosines for single precision. With ANSI, we'll generate sines and cosines, but they will ANSI only allows double precision operations, so you need the typecast to make it single precision. If you use ISO, you do get a floating point option, because that's one of the nice things about ISO-C. Whereas now you can get the ARM optimized single precision result. And again, it supports MATLAB, Simulink, and Stateflow. But you've been able to create those optimizations yourself using code replacement technology for several years. What's new with this release is we actually are supporting the high-level blocks, the DSP System Toolbox blocks for things like FIR and FFT. And so instead of an ANSI-C FIR, you now get the ARM optimized FIR. Just to show a quick example, I'll run a simulation of a filter where you can look at the spectrum analyzer and see that we're passing a 1 kilohertz signal and attenuating the rest. So again, we'll say that this is our expected behavior. Let's look at the code which I generated a few minutes ago to see what the code looks like. You can see we have a lots of ANSI-C for this filter, which is inside the FIR subsystem. But what if I want optimized code? Well, for this, again, it's simply a matter of going to the configuration parameters of embedded coder and saying Cortex-M. Now, if we generate code for this, you'll see that the code, a large chunk of ANSI-C code was simply replaced by a nice call to the FIR for this filter. So to obtain the code, you would download a hardware support pack shown here. You would install, go to MATLAB, say add-ons, get support package installed from internet, and you would then be able to grab the support packages. Now there's 3 support packages. By that I mean the capabilities to target ARM are provided in three packages. The first shown is the DSP System Toolbox support, which if you have embedded coder will let you generate optimized code for the basic math and the DSP filters. But as you can see, it doesn't include drivers or pill support. It just generates code that can work with any CMSIS compiler, and most of the ARM Cortex-M compilers are CMSIS compliant. If you don't need the DSP support and just want basic math, you could download only the embedded coder support, which does include an automated integration with ARM GCC to build the code and an automated integration with a QEMU emulator to execute the code on the host for Cortex-M3 parts. The third package, we didn't want to just produce code, we wanted to give you some hardware connectivity. So we added a couple I.O. blocks, analog and digital I.O. for the STM32F4 discovery board. So again, you can add those blocks to your model, compile it with ARMGC, and if you have that mini USB connector between the host and the board, you can do a pill test on Cortex-M4. Now these packages all work together, so if you wanted to do a DSP optimization test with the discovery board, then that will all work in a nice manner. As you can see on the bottom, ARM offers an additional integration, a much richer IDE integration with their ARM MDK for Keil and Microvision. This would support automated project build, pill testing, and quite a bit of other features. ST provides a much fuller support package for the STM32F4 devices. They're working on additional devices, and they support a variety of compiler tool chains for that part. To wrap up, that's the basic features you get with MATLAB and Simulink. I will now turn this over to Johannes Bauer of ARM Corporation, who will describe the ARM MDK integration in greater detail. So thank you.
Thank you, Tom. I'm Johannes Bauer from ARM and would like to tell you about the integration of our Keil Microcontroller Development Kit with MATLAB and Simulink. First of all, let me quickly introduce the ARM Cortex-M series processors. They are the little embedded siblings of the Cortex-A application processors found in mobile phones and tablets, and are similarly developed by ARM and then licensed to our partner companies, who put them in their microcontroller products. By the end of 2012, our partners had sold more than 2.2 billion devices with Cortex-M cores, serving all embedded market segments. There currently are 4 Cortex-M processors. Cortex-M0, targeted at classic 8 and 16-bit applications at lowest cost. Cortex-M0 Plus is the newest member of the series, with lowest power and outstanding energy efficiency. Cortex-M3 is targeted at classic 16 and 32-bit applications and is offered by our partners with feature-rich connectivity. Cortex-M4 has integrated function units for digital signal processing with accelerated SIMD instructions and floating-point logic. These processors provide scalable performance, real-time response, and a coherent architecture across applications. To simplify working with Cortex-M-based microcontrollers, ARM has created the Cortex Microcontroller Software Interface Standard, CMSIS. It provides a common software layer for various tasks, from device setup and configuration over real-time OS definition to debug access. Most interesting for this webinar is the CMSIS DSP library, which contains more than 60 operations commonly used in digital signal processing. This library is optimized for the Cortex-M architecture and makes full use of the core functionality. The Keil Microcontroller Development Kit is ARM's development solution for Cortex-M-based microcontrollers. It contains the Microvision IDE and debugger and the ARM C compiler in one powerful, yet easy-to-use bundle. MDK brings everything required for developing embedded applications: device support and example files for more than 2000 ARM microcontrollers, full CMSIS support, and an extensive middleware package for shorter time to market. To round out this software offering, ARM provides a wide range of development boards for various Cortex-M chip vendors. Together with the U-Link debuggers, they provide the best user experience for fast and efficient code development and debugging. The MDK link to MATLAB and Simulink is available as a free download from Keil.com. It enables MATLAB to create projects that can be automatically built and makes use of the device support and debug connectivity in MDK. It supports processor-in-the-loop testing as described earlier by Tom. For this, the generated code is automatically downloaded to the target platform and stimulus data from MATLAB is processed on the target microcontroller. Any results and sensor input is fed back to MATLAB to be compared with expected values. I would like to give you a quick demo of this now, using MATLAB, MDK, a U-Link Pro debug adapter, and a development board with a STM32F400 Cortex-M4 microcontroller from STMicroelectronics. I am running MATLAB with the optimized code generation for ARM Cortex-M targets using the CMSIS DSP library as well as the MDK link. It ships with a small Simulink example that we will use to show how all the pieces work together. When I press the Run button of the example, the code generation is triggered. Embedded Coder creates C code, which is put into an MDK project for the selected target platform. Once it is complete, MDK is called to build the project. Since this is a small example, the building happens very quickly. When I bring MDK to the foreground again, you can see how all the required files are put into the project structure. With a key press, I can start running the generated code. It is now downloaded onto the microcontroller and executed. In this example, I can open a diagram window that shows the value of an analog input channel of the chip which is connected to a potentiometer. You can see the value change when I adjust the knob. This is it in a nutshell. Code generation from MATLAB and Simulink used in conjunction with Keil MDK for quick validation and results. And now we can hear directly from ST regarding the STM32F4 integration.
Hello everybody, my name is Laurent Dessenier and I work for STMicroelectronics in the microcontroller division and I'm part of the marketing team. Today I'm going to tell you about how one can generate code for STM32 microcontroller using MATLAB and Simulink. What I'm going to demonstrate is the result of a common initiative between three companies, MathWorks, ARM and ST. Thanks to new software bricks like CMSIS DSP library targeting Cortex-M core DSP instructions, thanks to Peripheral block set for STM32 microcontrollers, and thanks to automation of compiler IDEs, embedded developers can now have a brand new way to handle their embedded developments with model-based design. This approach is bringing significant benefits in terms of quality, costs, and development time by proposing a step-by-step approach, switching progressively from simulation to really hardware-executed code. STM32 MCU portfolio is wide, with several series, all based on a common set of peripherals and architecture. We think this initiative with MathWorks and ARM is fitting well our F3 and F4 series, both using Cortex-M4 core with DSP instructions, and especially audio and motor control applications. Let's dive into the demonstration of this initiative. As said, user can progressively switch from model to hardware-executed code. For this demonstration, we'll use a model for a motor control application. Here is a simple description of such model. It includes four main parts. First one is the motor, a motor simulated model. Second one is the field-oriented control regulation algorithm that will run, actually, in the targeted STM32 processor in the end. Third one is the system inputs with simulated data. And last one is the diagram system analysis to verify the system response. Embedded processor algorithm is usually state machine development based on Stateflow diagram, as shown here on the right. Now let's dive more deeply in a real model, directly under MATLAB Simulink environment. This example includes Simulink motor model for the motor, which is delivered with STM32 motor control starter kit. It is driven by phases current generation model, depending on computed current values from reference model. Reference model is algorithm based on Park transformation process. System inputs is a speed instruction level from 0 to 300 rotations per second. Now that we have our model ready, it's time for the second step, simulation and test on the PC. The goal here is to get a reference on what response we should get versus the inputs. Let's issue this simulation test in the demonstration. First of all, we select curves to be displayed, phases, voltage and current, and actual rotor speed versus speed set point. Then, we set the duration of simulation and press the Run button to start it. We can see in the curves that the model is behaving as expected. So now we are fine with our model. We now leave the pure simulation and have part of our model, the processor 1, executed directly by the STM32 microcontroller. The goal here is to check if the hardware has the same behavior as the simulation. This is the processor in the loop functionality. This is fine to get STM32 in the loop, but it's even better if we can benefit from its Cortex-M4 DSP instruction set. This can be done through the ARM CMSIS code replacement library. In this sample, you can see a cosine function actually replaced with direct real DSP instruction call, which makes it much more efficient. Let's go to this step on our real model. We must change reference model configuration to PIL, processor in the loop, to be able to generate STM32 target code. We also have to set model parameters configuration, to select Keil toolchain environment, compiler optimization options, and select ARM CMSIS code replacement library. Then we run the PIL simulation. Embedded Coder has generated optimized STM32 C code, which is automatically built and downloaded into the target using Keil environment. Embedded Coder has generated reference model C code, including code replacement library directly. We also configure PIL to handle communication through UART to communicate between the STM32 and the PC. Keil toolchain builds a library that handles this communication. Code replacement report tab of code generation indicates substituted functions with this code replacement library. MATLAB calls Keil Microvision IDE a pop-up window asks you to wait for IDE to start. Then Simulink uses serial communication link to send input data to the STM32 target. STM32 target computes data and sends back results to Simulink for user to compare with pure simulation results we previously got. We are fine with the regression algorithm executed by STM32. Let's switch now to the final step in the code generation process. STM32F4 Simulink block set library has been developed to use peripherals as input or to generate motor control commands. Model reference must be PIL configured to generate STM32 target code. Its configuration parameters setting set replacement library and toolchain optimization. But reference model parameter must not be PIL configured. Configure peripherals block sets like GPIOs, ADC or timers. For instance here, ADC1 is regular multi-channel configured with DMA. Acquisition is time-triggered. ADC1 channels 11 to 13 are actually used to read motor phases current. Timer 4 block set is configured for encoder as timer 8 for PWM generation. Finally, press Build button to generate application C code. Embedded Coder generates code and code report, and Keil toolchain builds the project. MATLAB calls Keil IDE that programs and starts application on STM32 target. Everything runs fully on STM32. Here we are, a model programmed into STM32. Let's have a look to a video that shows this running live. Through this presentation, we saw that STM32 users can now choose a totally new development method that is reducing development time and cost, increasing quality, by using models through MATLAB Simulink. Even better, the generated code is STM32 optimized. In the end, this brings a lot of benefits for developers.